Good morning, and this morning I'm coming to you from the Hilton at 5711 West Century Boulevard, Los Angeles, California. Yours truly, Dolphy Gilpin, in continuity now with the amazing 5 cos 12 matrix. And we know that in our last communication we said that we would have probably go on to something else, but it seems we have not accomplished what we have set out to do with our AMZ 5 cos 12 matrix, so we are continuing. All right, so what's happening here this morning? We are doing some electrical circuit analysis, and we are using some of the component 2 cross 2 breakdown of the AMZ 5 cos 12 matrix. Notice we had 2 cos 2 breakdowns, 3 cos 3 breakdowns, 4 cos 4 breakdowns, and so on. And so this morning we have synthesized a 2 cos 2 mesh circuit from the breakdown 2 cos 2 components of the AMZ 5 cos 12 matrix. So let's proceed with our analysis here. So we have drawn a circuit here, and notice now that we must be able to transform from a linear representation into a metrical representation, and vice versa, from a matrix representation into a linear representation. So here we have the linear, let's choose one first, the linear representation, and then we'll use the matrix representation afterwards. So we have now V source 1 equal 15 volts, R equals 10 kilograms, 10 kilo ohms here, and R3 equals 5 kilo ohms, V source 2 equals 10 volts, and the loop now IA and the loop IB, and here we have 5K, and R2 is equal to 5 kilo ohms. And since I'm assuming here now that we are dealing with at least some students who would have been able to competently put in now these matrix from the components, that I don't really have to go over every little details. So I'm applying now the Kirchhoff voltage law to the mesh A and B, mesh A and mesh B. And in mesh A here, we have now that V source 1 equal V1 plus V2. So here's V1, and here is a V2. This is a V source 1, 15 volts. And in mesh B, which is mesh B here, we have now V source 1 is equal to V1 is equal to V2 minus V2 plus V3. And that's equal to minus V source 2. Next, we write the device current in the terms of a mesh current, and then express device current in terms of mesh current using Ohm's law. So using Ohm's law, now we have known that V1 is equal to I1 R1. So here's V1 equal to I1 R1. V2 is equal to I2 R2. V2 and I2 is equal to 5 kilo ohms. V2 is equal to I2 R2. And so now that it's equal now to R2 into IA minus IB, which is equal to now 5 kilo ohms times IA minus IB. And similarly, we say now that V3 is equal to I3 R3. And here we have V3 here, and this is I3 going like so. So we have V3 is equal to I3 R3, and that's equal now to R3 I3 minus now 5 kilo ohms times IB. So that now we can now write, we can now substitute the preceding voltage into the Kirchhoff voltage law and find that we found earlier. Now mesh A is equal to V1 plus V2 equals 15 volts, and 10 kilo ohms times now IA plus 5 kilo ohms times IE minus IB, that's equal to 15 volts. So this is V1 and V2. And mesh B is equal to minus V2 plus V3 equals minus 10 volts. So that now minus 5 kilo ohms times IA minus IB plus 5 kilo ohms times IB is equal to minus 10 volts. And from this, we have now that mesh A here, 5 kilo ohms times IA minus 5 kilo ohms times IB equals to, minus 15 volts. And mesh B minus 5 kilo ohms times IA plus 10 kilo ohms times IB equals minus 10 volts. And now we convert now this equation into the matrix form. And we get now that 15K, this is now R11, this is now R12, and we use it from here, R11 is equal to 15K, which is equal now to 10K here and 5K there, we had it, R11, and R12 is equal to minus 5K. The resistance common to 1 and 2, which is now 5K. Now R21 minus 5K, 2 and 1 minus 5K, and R22 is equal to 10K. And this is now time IA, current IA times IB, and this is equal now to 15 volts minus 10 volts. Now we could use a graphing calculator or a metrical software to give the mesh current IA IB equals now to minus 8 milliamps and minus 6 milliamps. So what I've done here, we have used now the components of the breakdown, of a certain breakdown of the amazing 5x12 matrix, and we have synthesized a 2x2 circuits, and we have represented in the linear representation as well as the metrical representation. And here's the metrical representation, and here's the linear representation. So as we continue, we have now, with this calculated mesh current, you can now find the device current. And we have now that I1 is equal to IA equal to 0.8 milliamps, and I2 is equal to IA minus IB equal to 0.8 minus 0.6 milliamps, that's equal to 1.4 milliamps. And to complete the analysis now, we use Ohm's law and say now that V1 is equal to I1 R1, that's equal now to 0.8 milliamps times 10 kilo ohms, that's equal to 8 volts. V2 is equal to I2R2 is equal to 1.5 milliamps times 5 kilo ohms, that's equal to 7 volts. And V3 is equal to I3R3 is equal to 0.6 milliamps times 5 kilo ohms, that's equal to minus 3 volts. And here we have just drawn the circuit again, and we have to be able to put in these R11 and R12 and R22 and R21 from the matrix representation. So once again, we'll have to be able to go from the matrices representation into the linear representation, and from the linear representation into the matrices representation. So we'll continue with a 3x3 matrix mesh circuit analysis, and as usual, we have been taking it now from the breakdown of the amazing 5x12 matrix. So let's just take a break, and then we come on to a 3x3 synthesis from component breakdown of the amazing 5x12 matrix.